Do 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 do. Do 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 do. Do 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 do. Do 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 do. Do 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 do. We're back. You can see that was a nice little Cause of the Wind, Moana 2, and my now Zoom background. I'm very excited to watch this movie with people next week. Very, very fun. So tonight we're going to talk about Turkey Day searching. This is a slightly interesting application of computer science for coding missions, and also it'll be the penultimate episode. The coding missions finale will be Cardinality on Advent, and that will be 2 weeks from now. So this episode is sponsored by Moana 2. And more importantly, also, it's very important to understand why we have searching algorithms. So you know about, DFS, BFS, linear search, Radix Search, and all these different, searching algorithms, binary search even. It's how to apply it to real life. We'll explore how far we'll go with regards to searching algorithms. And more importantly, just like Moana, we'll discover new ways to apply searching. Enjoy the episode. Also, happy Thanksgiving for those who celebrate, and enjoy the turkey and Thursday night football. So here we go, guys. So while the episode loads, of course, I just want to talk about something very important. I'll be going to Latin America with my family in December. That's why I'm ending decoding missions a little earlier. I also begin a mission soon for my church, which is fantastic. And praise the Lord, it's a good stuff. So yeah, this is Coding Missions episode 9. It's basically both based on Pocahontas, the turkeys, good stuff. So Cause of a Win from Pocahontas was the first ever episode that really taught me about searching, and most importantly, searching what's within your heart, also what's within around the world. So without further ado, here's the episode. Happy Thanksgiving! So we'll go for binary search today, linear search, DFS, depth first search, BFS, breadth first search, Radix search, and many more. Knowing your searching algorithms will be critical for any data structure-based interview. It'll help you locate your butterball Thanksgiving turkey faster. This is binary search, which is runtime O log n. Let's apply binary search to find where Thanksgiving turkey is hiding. Here's some important boxes number. The turkey is found in the median of the numbers. You have 9, 95, 11, 28, 20, 24, and 3. For the Pocahontas movie, year out, Thanksgiving date for this year, and also number of turkeys I personally already share with my church friends and companions. So, think about how binary search works. I'll annotate a little bit here. So binary search works like this. It's very, very straightforward concept for the most part. Yep. So you have an array here, right? And you have a bunch of elements. Let's say, for example, n, n plus 1, n plus 2, dot, 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 f. So the concept of binary search is the following. We split into 2 partitions, low and high, and then swap compare until we find median. That's the concept of binary search. We split into 2 partitions, low and high, and we swap compare until we find the median. Just like Moana and Maui. Moana goes in the low end, and Maui goes in the high end. We are back. How far I'll go? Boom. There's Moana. So that's what I love about binary search. It's really, really quick. It's O log n. It's really fun to watch. So let me just save this real quick from my drawings. I'll clear annotations, and we're good to go. So that'll clear the annotations, pretty much. And we're good to go. So continuing on the episode, we will clear our annotations. So here's the solution for the binary search. We have the box of numbers 19, 95, 11, 28, 20, 24, and 3. From Pocahontas movie, Clouds of a Wind, Thanksgiving Day, and of course number of turkeys I personally shared with church friends and companions. We sort the array first. So always make sure the array is sorted when you're running binary search. Then partition to two, pieces, low, mid, and high. Of course, when the low pointer is lower than the high pointer, when Moana is, trailing Maui, if we found the element is higher, we assign a new high element and vice versa. So using binary search, we find out that the turkey is found in box 20. There you go. That's the solution. Found the turkey in box 20. Next, we have linear search. Let's apply linear search to find the biggest pumpkin weight for a pumpkin pie. So I actually went to Costco to do it with my family and also with Ponyo. And we found out that there's actually quite a bit of pumpkins going around. The most heaviest pumpkin is almost at 14 pounds, which is huge pumpkin. And as small as at 2 pounds with like a little sugar, sugar pie pumpkin. So let's apply the very basic concept of linear search to find the pumpkin pie weight. So here's the linear search solution. We'll compare each weight to the previous and then swap it out of order. So do another quick annotation right here. So do a quick little stamp here. Star. So pumpkin 1 and 10, okay, good. So I start both of these. 10, 11, good. Start one of these. 11, 14, star, good. Oh, this one's not good. So I gotta switch to 2. Gotta do 9, and then 14, okay. 9, 13, good. So then gotta switch this again. So I gotta switch this again. So I gotta change the number here a little bit. So you gotta change the number to now this order. So 2, then 9, then 10. Whoops, I can make it a little bit bigger here. Yeah. Uh, whoops. 11, 13, and 14. So you make sure it's ordered. So just like similar to binary search is ordered, and now we're good to go. We know that the biggest pumpkin is going to be pumpkin number 6, pumpkin number 4 at weight 14. So that's your biggest pumpkin. So there's your result for the linear search. So linear search is of course ON solution. The worst case scenario, it's always backwards. If you want to find, for example, the biggest pumpkin weight for pumpkin, the smallest pumpkin for pumpkin pie, the worst case scenario would be 14, 13, 11, 10, 9, and 2. You have to go all the way to the end of a pumpkin patch to find the smallest pumpkin weight. So linear search is not used often because of that, because it's very easy to manipulate. But binary search is basically, split into 2. There's something called trinary search, split into 3. You basically do n plus 1 over, so you do n plus 1 over the floor of n to find the search algorithm. So this is a general search formula. Partition. You do basically n plus 1 divided by 2. So you do basically the floor of n plus 1 divided by 2. You generally get the search formula right here. And there you go. That's your linear search. So clear all annotations, and we'll move on. So now I'm going to go for the first graph algorithm, depth first search, or DFS, and runtime is OV plus E. So the number of vertices plus number of edges. So I have exactly 1, 2, 3, 4, 5, 6. So 6 vertices plus edges of 1, 2, 3, 4, 5, 6, 7. So this is going to be O of 6 plus 7, which is constant 13. So it'll be O of 13n, which is n. So it's linear. So let's apply DFS to see which store to get a mashed potatoes and gravy. The store is the last node after applying DFS. So here's a very simple directed graph. 1 represents Costco, 2 represents Sam's Club, 3 represents Publix, 4 represents BJ's, 5 represents Trader Joe's, and gotta have a Wawa for number 6. So I'll give you guys a few minutes to apply DFS, and I'll give you a solution later. While you do so, let's talk about some stuff in regards to graphs. So there are generally 3 main types of graphs in any computer science program. There's something called the DAG, the directed acyclic graph. This is the most common version. They have something called a simple directed graph, SMG, simple directed graph. So SDG, simple directed graph, which is this one. And of course, the most complicated is bidirectional graph. You know how you get, Facebook, Instagram, or, Reddit, Weixin, whatever, social media, connection friends of friends. We use bidirectional graph for those. So bidirectional graph works like this. You have a circle, you have another circle, you have an arrow, I believe, going this way. Whoops, I don't want to do that. You have arrow going this way. You have another arrow. Wait, what am I doing? Sorry, long day. You have bidirectional arrow going this way. There you go. That's a bidirectional graph. And bipartite matching is a very good example of bidirectional graphs that works very well. So there are the 3 main types of graphs. All right, let's move on to solution. Here's a solution. We apply DFS to see which store to get our mashed potatoes and gravy. The store is the last node after applying DFS. So let's go for DFS, shall we? Yes. So we're going to do check mark this time. So let's see. Neighbors of node 1 is 2, 5, and 4. Neighbors of node 2, I'm going to use a different emoji, is 3 and 6. 3 has no neighbors, that's none. 4 has no neighbors, that's none. 6 has no neighbors, that's none. And 5 only has one neighbor, which is 4, using star. So using that approach, we can get something called an adjacency list, which is basically, the list of the nodes that are adjacent to each other. For example, Moana's case, Moana's island is adjacent to Teferi's island, or Maui's island is adjacent to somebody else's island. It's like almost like the concept of islands. So the really fun LeetCode problem, number of islands or number of connected graphs, is used with DFS. So that's basically how I got my role. My job is by using that LeetCode. So very important to understand DFS really, really well. Also, this book, always a classic, coding interview with this woman, Gail Lackman McDowell. Very, very important. And that's basically how I got motivated to do these algorithms. I used to really suck at algo, but now I'm getting better at it now. So we applied DFS, which we already have, and found a solution is at node 4, which is BJ's. So get your gravy and mashed potatoes at BJ's. There you go. So one little warning with DFS. This only works for simple graphs and directed graphs. This will not work for bidirectional graphs. And neither will BFS, breadth first search, as you'll see next. So let's just clear our drawings. X this out. All right, here's the second graph. BFS, breadth first search. Which level-based search? It's also O of V plus E. So now let's apply breadth first search to see which store can get cranberry sauce. The store is the last node after applying BFS. So once you have the same graph, you know, 1 for Costco, 2 for Sam's Club, 3 for Publix, 4 for BJ's, 5 for Trader Joe's, and 6 for Wawa. And while guessing about the solution, I'll give you another idea about what BFS does. Whoops, I did not mean to do that. That's not what I intended to do. Whoops. There we go. So I'm going to show you what BFS is doing. This is a really simple example of BFS, a binary search tree. So just remember, I just have very simple tree here. I don't know, something stupid like this. And you got a bunch of arrows here. It's hard to draw graphs on Zoom, but we'll make do. So general for BFS, and Gail Meckman McDowell mentions this. So your general search space for BFS is the floor of D over 2. D is the depth of the tree. So for example, you have here depth equals 1. You have here depth equals 2. And here you have depth equals 3. So here, the depth of this tree would be, sorry, the depth of this tree would be floor of 3 over 2, which is going to be 1. So you want to find basically your DFS like this. So you want to find one layer of DFS over here, another layer. So it reminds me of chemistry almost, you know, like the neutron, then the electron, then a proton. So a little bit of chemistry type of stuff, a little bit of, you know, physics regards to BFS. So DFS is depth first search. BFS is breadth first search. So DFS, think about adjacency list. BFS, think about layer queues. Essentially, it's layered queues and adjacency lists. That way, you'll never get it wrong in the coding interview. Well, hopefully, it's not as harder than that in the coding interview. So yeah, that's enough for BFS. I'm gonna show you the solution now for the thing. So here's the solution. So as I mentioned before, we need an adjacency matrix this time. That's a difference. So once again, I'll show you the adjacency matrix with the green check. So let's see, adjacency matrix, we got 1. Okay, 1, you have the layer of 2, 5, and 4. So you see right here, 2, 4, and 5. Then for node 2, you only have layer of 5 and 6, which I'll change a different emoji to X. 5 and 6. So 2, you have my apologies, 3, 5, and 6. Sorry, 3. Sorry, go back. 3, 5, and 6. So imagine doing a midterm, how hard this would be. 3 got nothing. 4 got nothing. 5 only got 4, so I'll change the emoji to heart. 4 and 6 got nothing. That's it. So applying BFS, I look at the first layer. Change the color here. This is a little bit weird. Change the color to blue. Got here, layer 1. Here, you got layer 2. Here, you got layer 3. So essentially, you want to find the result from layer 3. So applying BFS, you have 1 neighbor to 2, 5, 4, then 2 to 3 and 6, then 2 to 5. Okay. You'll find out eventually in the end that node number 6 is your solution. This is the farthest out after applying BFS. And there you go. That's the BFS solution with the adjacency matrix. So the solution part 2. We apply BFS to get a result, which is node 6, or gotta have a Wawa. There you go. All right. Something really cool that I use in my work for member lookup is called Radix Search. And I help a lot with Python, pandas programming, and also just with tree structures in Java as well. So Radix Search is actually really cool. I learned this from BU and also used quite a bit of it in my Europe computing and also my day job right now for member lookup. So you got, you know, the nodes TURKEY, Turkey, and runtime is O of 2 log n. And a quick reason of how the runtime works, just to give you a little bit of a math assignment. So how do you get the runtime of Radix Search? Well, you have O log n for each binary tree. You have O of 1 constant time for lookup. Then you have 2 for each left-right tree, subtree. So total, you get 2 times O of 1 times O log n, which is 2 O of 2 log n. That's it. That's your solution. That's how you get the runtime. So if you're in an interview asked, how to get runtime, make sure you can do the math. Very important. The math is very important. All right, now the math is over. Whoops, I keep doing this. The math is over. I can now give you the solution. So the math is over, give you the solution. So wrap up Thanksgiving, we'll apply a form of tree search called Radix Search with digital search trees. So for every digital search tree, it's basically like a decision. So you have either 0 or you have 1. It's basically a decision tree with bidirectional graph. So 0 here or 1 here. And here you only have one choice, 1. That's it. That's how you get the Radix search. So it helps really well with circuits and member lookup. Basically, if a member is in this thing or a member is not in this thing. If a member is in this client or a member is not in this client. So it helps a lot with, pick and choosing. For example, if I watch Moana 2 or watch Wicked, right? Or if I want to root for the Celtics or root for Golden State. Or do I want to date this girl or date that girl? It really comes down to understanding Radix search in terms of choices. And always choose the right. Very important. So yeah, the node containing the letter that represents the house at the end of Radix search will contain a cornucopia, which is a big, storage for Thanksgiving food, historic Thanksgiving food. So that's it. To wrap up Thanksgiving, we're gonna have basically find the food from the Radix search. So my roomie Graham and also you know, former GFs, Dave, former GF, we all work really hard on understanding circuit design and especially with regards to soldering and 3D printing and engineering stuff. Um, I wish I chose 1 than 0. So yeah, relationships and choosing the right is important. And the concept of this rate search is very important in regards to understanding how the trees work. Anyway, here's the solution. So to wrap up Thanksgiving, we'll apply a form of tree search called Radix Search. Yeah, we got that. To apply Radix Search, all right, we have array beginning with T, then TRU, then TRUY, then TRUYE, and TRUYEK. So there you go. K is your solution for the Radix Search. The cornucopia is found in the house K. So you ask, what's the best case scenario, worst case scenario for Radix Search? Well, let me show you guys. The best case, worst case scenario for Radix Search. Here's the worst case scenario. You got basically a linked list. This is the worst case scenario for Radix Search. You have to search for a linked list, which is horrendous. You have to basically compare this to this, this to this. This is the worst case scenario for Radix Search. Never ever get into this situation for Radix Search. Conversely, what's the best case scenario? A circle. Basically a triforce triangle. That's the best case scenario. So here's the best case scenario. So essentially, an infinite triangle is the best case scenario for Radix Search. Because no matter what, you'll be able to find the neighboring node. This is the best case scenario for Radix Search. So if you want to know more about Radix Search, I suggest you guys look at, Sedgwick and Wayne, Princeton, Boston University edition book, or look at Gil Lehman McDowell's Radix Search. And I'll see this chapter in I see Radix Search in chapter 10. And Gail does use a lot of Java, but her code is pretty easy to understand. She types two types of Radix. She has Radix Sort, and also she has Radix Search. So both Radix is basically think Radix as binary. 0, 1, 0, 1, 0, 1. Wicked, Moana. Wicked, Moana, Wicked, Moana. Democrat, Republican, Democrat, Republican, Democrat, Republican. Just think of a binary search. Black and white. That's all we have to do for Radix Search. So yeah, that was rather a quick and dirty introduction to Radix Search. It's a very complicated algorithm to code out loud, so I don't think anybody would be required to write Radix Search pseudocode in an interview. Just understand if you're given a tree, how do you apply Radix Search? That's really what it comes down to. So yeah. All right. Assignment for you guys to enjoy your Thanksgiving. So like and subscribe, if you're a subscriber, do the assignment. It'll help your interviews. So apply binary search, linear search, DFS, BFS, Radix Search to the following. To apply binary search to the Celtic numbers, Tatum, Brown, Smart, Horford, White, Holiday, Porzingis. And of course, apply linear search to Thursday night football teams and scores. New England Patriots 33, Green Bay Packers 14, Cincy Bengals 21, Detroit Lions playing really well, 46, New Orleans Saints 17, Kansas City Chiefs defending champions 51, and LA Rams 43. So apply linear search to that. Of course, it's a really easy graph. So then apply BFS, DFS for this really easy cyclic graph. And of course, awesome. Apply Radix Search to basic colors that will win from Pocahontas. So Pocahontas is married to John Smith, is part of Disney. John Smith understands the colors of the wind. There you go. That's your assignment for Thanksgiving. If you want to skip the assignment, that's fine as well. It's not mandatory, but help you with interviews a lot. So yeah, thank you. This is going to be it for Coding Missions episode 9. So finale will be on avant cardinality, which is one-to-many, main-to-one mapping. And I finally show you guys how to actually really understand what to do for the real world in terms of computer science and further analysis and conversations. So yeah, like and subscribe from the search algorithms. Also, if you guys have any ideas, where to go for Mexico, the Dominican, or Puerto Rico for fun places. I know I've been looking at Tulum, Cancun, Santo Domingo, and San Juan, but there's also really cool places as well. Ironically, these search algorithms helped me with my TripAdvisor flight planning for my Latin trip, and also it's really good. So TripAdvisor, fun fact, uses these search algorithms to help you find your best prices. Hotel Trivago as well. So if you ace the search algorithms, you can become an agent for computer science and also for travel. And after COVID, boy, do we want to go traveling, guys. So anyways, enjoy Moana 2 coming out theaters in Wednesday and your Thanksgiving. Thank you. It's Jason Liu signing off. Good night.